So Friday greetings everyone, or I should say Friday greetings digital world, virtual world. Today's topic is going to be really fun. It's on design patterns, and this topic connects really well, in my opinion, with the lecture on subsystems. So in my mind, you can think of design patterns as special cases of subsystems. And you'll see there are connections and overlap between the material we were talking about with object-oriented design and design patterns. Hopefully you can see some of the connections there and some of the overlap in material. But from a conceptual point of view, design patterns are basically just special kinds of classes and subsystems, in my opinion. And feel free to interrupt. By the way, I got some nice surprise today. 4 students came by my office hours this morning and collected their free laptop covers that they won from 2 labs ago. So that was fun. Yeah. So I think, yes, you can ask coursework questions at the end. I hope that you post your coursework questions also in the coursework questions chat or the channel on Teams. We're trying to get all the questions together there. And I also encourage you to post your questions in the lab helpers chat as well. The lab helpers are hoping to help with this as well. And yeah, but I can answer a few questions at the end of this too. Maybe. I don't know the answers to all the questions. Okay, so let's jump in. Firstly, there's some helpful reading on design patterns if you're interested. There's actually a book, another book. Let me just check something really quickly. That's not the only design patterns book. Yeah, that book does have a strange cover, doesn't it? I thought I updated this slide with another book though. There's of course more than one book on this topic. A very fun exercise it does. It looks like an MTV version of design patterns. Yes, let me just quickly, these are 2 books on design patterns. I guess I'm gonna go try using PowerPoint and see, well, let me just see here. Okay, so PowerPoint, save as. I thought I did this already, but apparently I didn't. Looks like I made some very last minute edits and I forgot to export them to PDF. So let's try that. That's a lot of slides actually. This is really 2 lectures. By the way, a very fun exercise would be to go to freetechbooks.com and type in design patterns and see how many books you get in response. That would be a very interesting exercise. If anybody wants to try that exercise now, that would be cool. And just let us know in the chat how many design pattern books you find in the freetechbooks.com. Oh wow. So it looks like I got a crash. This is the danger with trying to do this stuff live. It looks like I got a crash. Oh, that's so annoying. Ah. Okay, I guess I'm gonna try then the PowerPoint slides. Oh, is PowerPoint crashing on me too? Okay, let me see then if the export worked. Maybe the export worked. Oh, it worked. Okay, let me just shut down PowerPoint. So PowerPoint crashed on me. Force quit. It is a lot of stuff running on my machine right now, so maybe my machine can't handle it. Okay, so yes, I did update that slide. So there are two books. Actually, this book here by Gamma et al. Is the classic. That's like the classic book on design patterns, actually. How do I get rid of this window? Oh boy, Microsoft error reporting. It's chaos. It's chaos in the lecture today. So there are some helpful reading. Design patterns. What is a design pattern? So a solution, a set of objects and collaborations, that's also could be a subsystem, by the way, that addresses a problem which occurs over and over again and then describes a core solution to that problem in such a way that it can use the pattern over and over again. So there are situations that occur over and over again in software engineering, and there are essentially prescribed solutions to these problems, which is not very surprising. So a pattern provides an abstract description of a design problem and how a general arrangement of elements solves it. A design pattern identifies the participating classes and instances, their roles, collaborations, and the distribution of responsibilities. So you can see how this really fits in with the material on object-oriented design. But it's not very difficult to imagine this idea of certain situations coming up over and over again. In Java, you probably have noticed this in Java as well. So Java has built into it error handling for very, very common errors. And they don't call it error handling, they call it exceptions. So for example, if you're writing a program and it needs to read data from a file, right? You have to try to open a file and start reading data. And then if that fails, Java throws an exception, a file I/O exception or a file open exception, and says, hey, there's something wrong here. It's the same idea. So Java has anticipated problems inherent in the programming language. Problems that are extremely common that come up over and over again. It's the same idea here, except it's more abstract. It's here are some things that happen in software over and over again, and here are some recommendations about how we're going to address that. I like Java, actually. So a pattern specification has 4 essential elements. A name, right? So we need to refer to it somehow. A handle we can use to describe the design problem, its solution, and the consequences in 1 or 2 words, right? Having a vocabulary for pattern lets us talk about them with our colleagues and in our documentation. And you'll notice that the coursework recommends or mentions a design pattern called MVC. A design pattern has a problem that it solves, right? When do you actually use the pattern, in what instances, in what cases, in what contexts? Of course, a prescribed solution, and yeah, so what do we do about it, and then the consequences. So every design pattern has advantages and disadvantages, and so we have consequences to deal with whenever we use the design patterns. So there's a collection of design patterns. There's not just one. So they're grouped into different categories. And there's some of these categories, like the purpose, the group of that fits into the purpose. We have creational design patterns, right, that are kind of like factories for generating many instances of many different kinds of objects. We have structural design patterns, like things like bridges that try to interface between two pieces of software. And then we have behavioral design patterns. These could also be like almost like algorithmic in some ways, right? But they're really thought of in terms of their unique behaviors as opposed to structures or creational. And then we have different kinds that are thought of in terms of classes, patterns that deal with relationships between classes and subclasses, and then patterns that deal with objects. Remember, we have this objects versus classes versus objects theme coming up over and over again in software engineering, right? We had a few slides on this. Is behavior like iterator and observable? What does MVC come under? Okay, so we're going to get into the details now. Yes, I'm going to answer these questions as we go along. And let me know how I do. If you don't understand afterwards, like, or at the end, please let me know. Yeah. So one of the challenges with design patterns is there are a lot of them. So we certainly won't cover them. Actually, when I think of it, it's just like the UML diagrams. I don't remember how many UML diagrams there are. There are something like 40, maybe? Can anybody remember how many UML diagrams there are? There are a lot. I have a book. It's called UML Distilled, and it's something like maybe 100 pages of summaries of UML diagrams. And then you can buy a thick UML book that has, I don't know how many, but actually not all the UML diagrams are even used. Probably there are only 10 that are used in practice, with some exceptions, obviously. That's analogous to design patterns too. There are lots of design patterns, but there are some that are a lot more popular than others, really. So we're going to focus on some of the popular ones. There are probably like 10 that get used very often, and then the rest, nobody knows how often they're used. So how many design patterns do you really need to know? In my opinion, like, I don't have a very good memory, actually. I'm not the kind of person that can memorize things very, very easily. And so my answer to this question is you don't need to necessarily know or remember any design patterns, but what you need to be able to do is have a reference book at your fingertips that you can browse through whenever you think you need a design pattern. That's the way I personally operate. It's the same thing with programming. When I'm doing Java programming or C++ programming, I need a reference book. Even though I have many years of experience, I need my reference books. They're almost like emotional support. I just want to be able to open up a page, and I have printed books, by the way. I have them there on my desk always, and I'm always looking through and referencing them. I mean, I don't have to remember these things because the book remembers them for me, and then I can use my mind for other things. But my mind is not about memorization. I learned that a long time ago in high school. My mind is kind of an analytical problem solver. That's what my mind does. So how many design patterns do you really need to know? The most useful should be high priority theoretically, and then you might want to know that there others exist, and then the other ones are archived in a book, a reference book for whenever you need them. I've listed some of the more popular ones here: Adapter, Factory, Observer, Strategy, Builder, State, Singleton, and MVC. Oh, did somebody find one on freetechbooks.com? That would be cool if somebody did a search on freetechbooks.com and told us how many books there are on design patterns. We're going to talk about some of these today, some of these common ones. Right, and there's a lot you'll see throughout the slides. There are different URLs to resources. This is one of the good things about being a student today. There's so much free and accessible educational material out today. I mean, there has never been a time in our history where there's been so much free and accessible educational material. So software engineering is one of these subjects that benefits massively from all of the free educational material. And there are some nice YouTube channels just about design patterns. So really, in that sense, it's a great time to be a student. It's not, there are disadvantages too, but in the sense of how much information is at your fingertips, it's really good. And if I sit here and ramble for 24 hours and you don't understand what I'm saying, you can just look at somebody else's tutorial, right? It's not a big deal. So we have, again, these different categories of design patterns: creational, structural, behavioral. Right here we have the periodic table of design patterns. So this already gives you an idea that there are quite a lot of them. I don't know all of them, by the way. I know I have a book, but I don't I don't know all of them. But what I do know is I know about, in my head, the process of designing object-oriented software. That's the way my mind works. So I know my head knows how to put all these pieces together and solve a puzzle. So that's a good thing. So if you're not good at memorizing things, you can still be, a competent software engineer. Let's see. Okay, so here's another overview of some of the design patterns, right? This time they're classified by class versus objects. So class-oriented design patterns and object-oriented design patterns, right? Factory method, abstract factory, builder, prototype, singleton. So this is I like this classification table. This is really nice, actually. So all of these design patterns solve the problem of making things. All of these design patterns solve the problem of connecting things together. And then all of these design patterns solve some sort of a problem. So here, look, somebody asked about iterators. Where do iterators fall? So here is where iterators fall. So they're behavioral and they focused on objects. What was the other one? Iterator and observable. Where is observable here? Okay, observer. So observer falls into that same category. It is a behavioral which makes sense intuitively, and it is object centered. So this is a very nice overview table, actually. Here's a little bit of information about creational patterns, right? The abstract factory, an interface to create related objects without declaring the concrete class. That's an abstract factory. So you can see in the factory case, in all of the different categories, you have both the class-oriented design patterns and the object-oriented design patterns. So you have basically both versions, so to speak, across both categories. Builder is the same construction process that can create different representations. We have a factory method. So this is when you actually instantiate or defers the instantiation to subclasses. That's a very common one right here. Prototype is creating new objects by copying the prototype, which is kind of what I referred to in my previous lectures with the example of the car tire. I don't know if anybody can remember that. And then Singleton ensures that there's only one instance of a class created. It's not very difficult to imagine when you might want to use these and apply these. I like to think of Tetris as an example. Everybody loves Tetris, I'm sure, and plays it every day. But in Tetris, you need these objects constantly. You need new objects constantly that fall from the top of the screen. So wouldn't it be nice to have a design pattern that solves that problem for you? Well, yes, that's exactly what this is. It's a factory. It's a factory design pattern that solves that problem. So you need to be able to generate lots of these puzzle pieces, right? I don't know, every 5 seconds or something in Tetris. So you could apply a factory method to do that. Here are some overview of constructional patterns like adapters. Adapters provide compatible interfaces for classes that don't normally work together. Right? Bridges decouple abstraction and implementation so that the two can be independent of each other. So it's like essentially an abstract adapter. Say that 10 times fast. We have composite design patterns. Composite design patterns that put objects into a tree structure and represent the hierarchies. So that's like you could call that a hierarchical adapter. And a decorator that puts individual instances of dynamically, adding new functionality dynamically. So that one's a little bit more sophisticated, I would say, than some of the other ones. Facade, providing a unified interface to a set of interfaces. So that's like an interface to interfaces. And hopefully some of this is ringing bells for from the lecture on subsystems, by the way. Flyweight, use sharing to support large numbers of complex objects. Right? If you need something that's deals with large data sets and proxies, I think everybody's heard of proxies before, right? That's a very common word in computer science, right? Provide a placeholder for another object to access its controls. Now, this lecture is not going to go into detail about all the different design patterns. We're giving you an overview to start with, and then we'll jump into some details on a few specific patterns. But it would be like torture to go through all the design patterns, just like it would be torture to go through all of the UML diagrams. That would be really, really painful. Here are some behavioral patterns. There are 2 slides of these. Chain of responsibility. Give more than one object the chance to handle a request. Right? That's a very common behavioral pattern, right? That reminds me of a web server. Command encapsulates a request as an object. Yep, that makes perfect sense. It's not very difficult to imagine these design patterns in practice. Interpreter, converting problems expressed in a natural language into a representation. Right? You can imagine such a design pattern being applied to a search engine. Iterator, accessing objects without exposing the underlying representation. We talked about this in previous lectures on object-oriented design, this iterator class. Mediator, promoting loose coupling by preventing objects from referring to each other. So that's like a very abstract interface class. And then some more here. Memento, capture and display an object's internal state. Oh, that's a funny one. That's an interesting design pattern. It might be interesting to read why that's useful. It's not the world's most obvious one. Observer, yes, this is a very common one. So define a one-to-many relationship so that when one object changes state, all of its dependents are notified. We're going to talk about that one, by the way, in a little bit of detail. State, allow an object to alter its behavior when its internal state changes. For me, that reminds me of a finite state machine. A finite state machine is certainly a behavioral pattern. A strategy, define and encapsulate a family of algorithms. Let the algorithm vary independently of who is using it. There are lots of design patterns. Template method, define the skeleton of an algorithm and let subclasses redefine certain steps without changing the structure of an algorithm. That's a really cool design pattern. Visitor, define a new operation without changing the classes. That's pretty cool too. I can't imagine using the visitor one, but it sounds really cool. I can definitely imagine using the template method design pattern. So those are an overview of design patterns, and now we're going to talk about a few specific ones in a little bit of detail. Starting with the Singleton. So the Singleton, create a one-of-a-kind object for which there is only one instance. Right? That's not very difficult to imagine either. So for example, if you have a database in your application, you want to make sure that there's only one, generally speaking, I'm sure there are exceptions, but generally speaking, you want to ensure that there's only one database in your program, right? You don't want to copy a database because, well, there are two reasons for that, at least two reasons. One, as soon as you make a copy, they become inconsistent with each other. And secondly, you're going to waste a lot of memory, right? So there are certainly going to be instances where, no pun intended, where you only want one instance of a class or an object, right? So here are some other examples. Just one window manager, or one print spooler, or one database, or one game board. One instance of a game board. I guess all of you guys are familiar with these online games, right? So a Singleton has a single class in its own class diagram, but how do we ensure that there's only one instance? The solution is not that difficult, the naive solution. To ensure a class only has one instance, we provide a single point of access to it. And we need to have that one instance easily accessible, and we want to ensure that the additional instances of the class cannot be created. So well, we're gonna present how that works. But a common question that arises is, do global variables solve this problem? And yes, you can have one object that's declared globally, but this is not the most efficient, most efficient solution. Global variables are not encouraged, generally speaking, because of communication patterns. They make communication patterns very difficult to manage. So if you have a global variable that can be accessed by any part of the software, imagine the software has millions of lines of code. That means if you make a change to that global variable, you can't. You can't make changes to the global variable because you'll break the software. There are too many dependencies, right? So you want to avoid that kind of a solution. Right? If you try to change a global variable, you will generally break the software, and you don't want to do that. So really the key to solving this problem is to make the constructor of the singleton private. That's essentially the solution. So here's a class called Singleton, and look, the constructor is private, right? There's a constructor and it's private. And that's unusual. Usually constructors are public, right? That's the usual. And then you have one method called getInstance. And that method encapsulates the responsibility of instantiating the one singleton, right? If it just checks, if it hasn't been instantiated yet, it instantiates the object. Otherwise, it just returns the existing object. So it's a pretty simple solution in the naive case, right? And this is what it looks like in a UML notation with a class card, right? It has a private member variable, which doesn't follow Bob's coding conventions, by the way. It really should have an M underscore. I'll have to fix that someday. And singleton data, which should also follow the M underscore naming convention. And then you have these methods like single instance and singleton operation and generate singleton data and so on. Okay, so it can be more complicated, right? If you have a multi-threaded program and you're getting concurrent requests for access to a singleton, that might complicate things. So you have to make a thread-safe version of singleton, right? You have to make that getInstance method synchronized in Java. Otherwise, you could violate the single instance principle, right? So there are some subtle aspects to that need to be considered sometimes. Okay, any questions about the singleton pattern? It's probably one of the most common, almost definitely one of the most common. By the way, I hope that some of you are thinking, oh, that sounds familiar somehow. Like, have we encountered that before? We didn't encounter the word singleton before, but we encountered an object-oriented design principle that states, keep information about one thing in one place. And that is closely related to the singleton design pattern. They're not exactly the same, but basically, if there's some important information or important data stored in your program, you want to have one place to store that data. You don't want multiple copies of important data. We did it last year with Jason for one of the courseworks. Okay, maybe you did. That's cool. That's cool. Okay, so the factory patterns. And you can think of Tetris. I don't know why. I don't know why. I think Tetris is stuck in my mind now. But it is a good example. With the factory method pattern, we create objects without exposing the creation logic to the client and refer to newly created objects using a common interface. So there are lots of times when you need to construct lots of objects. They might all be the same or they might be different. And the factory design patterns are handling this offering solutions to these common challenges. So the essence behind the factory patterns is that they hide how objects are created and service the system independent of how its objects are created. So they encapsulate, if there's a somewhat non-trivial instantiation process, they just encapsulate that process. Class creational patterns focus on the use of inheritance to decide the object to be instantiated in the factory pattern. So it's not difficult to imagine a class hierarchy or an object hierarchy. A class hierarchy could be like the Tetris pieces, right? You can imagine a parent class called Tetris piece, and then you have children that are the different kinds of pieces, like one's the L-shaped piece, one is the straight edge, then you have the square piece. And am I forgetting one? There's probably there's that one that's like a stair, like a step, and those would all be children of the parent called Tetris piece. The factory method pattern can save you those awkward dependencies in object-oriented design by letting you define an interface for creating an object, but let its related subclasses decide which classes to instantiate, right? It's used when another class doesn't need or doesn't want to know precisely which objects it must create. So it's outsourcing the object creation process. Here's what it looks like in UML notation. Right, there's the creator object, and it has a factory method, and there's a concrete creator class and it also overrides the factory method, and then it produces these products. So in the case of Tetris, that's a concrete factory, right? We're instantiating real, so-called real objects like the Tetris pieces over and over again. But we could also have something that's more abstract, right? The abstract factories. It's a factory of factories. I don't know how often this one's going to be used, a factory of factories. But that is another design pattern, and it's used when you need an interface for creating related objects without specifying their classes. Right, so here's a UML example of an abstract factory. So it's actually a factory of factories. Here's a concrete factory child called Concrete Factory 1, very creative name. And then another one called Concrete Factory 2. So it's a factory of factories. And these factories create different products, right? Concrete Factory 2 creates product A1 and B1, and Concrete Factory 2 produces product B2 and A2, right? And those are both also child of abstract products. So that's an example of an abstract factory notated in UML. Here's a factory method pattern example. If we want to create different types of shape objects for our drawing editor, for example, you know how I love to talk about the drawing editor? So a drawing editor has to create lots of different shapes. So we have a class called factory pattern demo. It has a method called main, And then we have another class called Shape Factory, and it has a method called Get Shape with different types of shapes. But look, the Shape Factory outsources this business of creating different shapes, right, to a shape class, and then the shape class decides which shape to create, like circles, rectangles, squares, edges, polygons, triangles, and so on. And look, I don't remember UML diagram notation very well, so I put in a little note to myself. A filled diamond means composition, and an empty diamond means aggregation. Right, so I put in little notes for myself about what the different UML notations mean. Right, here's what that looks like as an implementation. Right, we have a class called Factory Pattern Demo. It's got the main method. It creates the shape factory. Right, it instantiates a new shape factory, so a real instance of a shape factory. And then it outsources all of this business of creating new shapes to the shape factory. So it asks the shape factory to return a circle, which is a kind of shape, and then it draws the circle, and then it asks for a rectangle, and then it draws the rectangle, right? And these shapes all have their own draw method, as you noticed. Here's our shape parent class, and it has a method called draw, which is empty, by the way. And then we have a child called circle that actually has a draw method. And then we have the shape factory constructor, right? So the this is the encapsulation that I'm talking about, encapsulating the construction process. So the factories check, basically they perform a test. What kind of shape do we need to create? And then we find out, depending on what the request was, we return the shape, right? So it encapsulates this construction process of many different kinds of things. So it's pretty simple, but it's very, very useful. This one I would say is very useful. Yeah. So the classes that participate in the abstract factory pattern are the abstract factory to declare an interface for operations that create abstract products. We have concrete factories that implement operations to create concrete products. We have abstract products, declares an interface for a type of product object. And then we have the concrete. This could also be called concrete product. Defines a product to be created by the corresponding concrete factory. And then we have a client that actually uses those, the abstract factory. So some more details about the factories. And now you know all about the factories today. The abstract factory class determines the actual type of concrete object and creates it. Actually, this all is embedded in the source code anyways. It returns an abstract pointed to the concrete object it just created. And this prevents the client from knowing anything about the actual creation of the object. It's just outsourcing that responsibility. The objects of the concrete type created by the factory are accessed by the client only through the abstract interface. To add new concrete types, modify the client code to use a different factory. I think this code here is a very, very nice example and summarizes it really well. Okay, I think we've said enough about factories, I think. I actually think we're going to skip the pizza factory example because I think it's pretty clear what a factory does, right? There was the shapes example that we just saw. I don't think we really need to go into the details about a pizza factory, another example. Okay, I think what we'll do is we'll take a break now and we will come back in 10 minutes. What do you guys think? Does that sound like a good plan? And we will start with the adapter pattern when we come back in 10 minutes. So let's do that.